Okay, welcome everyone. Hope everyone had a good Thanksgiving. Let's get started with some course announcements. So first of all, problem set 3 is up. It is available on Slack, and I'll be posting it on my courses. Second, an announcement that over the course of the course, we will drop the lowest 2 scores on individual problems. That's not on problem sets, but the lowest 2 scores on individual problems for any of the problem sets over the whole course will be dropped. There are office hours tomorrow at 10:30 for Vincent and Friday at 10 a.m. as usual for me. Are there any questions about anything to do with the course? Problems are weighted equally on the problem sets. In answer to the question about grading scheme for problems. Does that answer your question? What does one need to do to get 10 points on a problem? One needs to have a correct proof. And so there are points dropped from a problem if the ideas are incorrect or they're not expressed in such a way that it leads to a logical proof. There is no, it's not something that could be automated. Grading proofs is to some extent a judgment call. This is the way that it's done, for example, on any proof-based test like the national or international math Olympiads, which obviously the problems are much harder, but this is like grading proofs in that way. Yeah. About the problem sets, are we expected to be done prior to exams? I believe the last problem set will be in the last week of the course. I can let you know about that, but just work out 2 weeks. There will be 6 problem sets. The last problem set will be, I believe, the last week of the course. Does that answer your question? This problem set should be a little bit easier, hopefully, than the previous one. It was 1 day later because of Thanksgiving. Are there more questions? If you have any questions about the grading on the problem sets, feel free to contact me or Vincent. We can certainly take a look again at anything that we might have graded incorrectly. Yeah, and there is no one right answer on any problem in the sense that there isn't just one way to prove something. And if you have a correct proof that wasn't the one that I was thinking of, you will get absolutely full credit as long as you write it out correctly, just like any other proof. And I've been really excited to see proofs that I hadn't thought of on many of these problems. It's just really fantastic. You don't get extra credit for coming up with something that I hadn't thought of, but you get just as much credit as any other correct proof because there's always so many different ways to get to the answer in math. Yeah, if you have a particular question about grading, then absolutely send me a direct message on Slack. I am very happy to look at anything for any of the homework. Okay. Is it possible to get feedback for problem set 2? So there will be, you mean solutions to problem set 2? Yes, there will be problem, by the start of next week, I see. I will talk to Vincent to check when feedback will be available, but hopefully, yes. I do encourage everybody to look at the solutions for problem set 1, because I spent a while trying to make those a model of how I think that proofs should be written up. That's not to say that you should have written them exactly like that. There are so many different ways to write them, but that I tried to write them in such a way that it was an example for how to write a proof, in addition to the actual the actual substance of the proof, right? I guess a special note about problem set 3, don't really worry about making matrices beautiful. Writing matrices in LaTeX is really, I guess some of you may have seen that in problem set 2 as well. There are many ways to write matrices in LaTeX. Feel free not to spell out literally all the entries of a matrix. I sometimes just write matrix A, ij. If I'm trying to write a full matrix, I don't have to write out all the columns and rows. How do we know when a proof is done, or if there's some edge cases we haven't thought of? This is such a good question. And honestly, it's just experience. This is something that one gets through having looked at a lot of problems. I'm sorry that it's not very satisfying. And that's one of the reasons why this course exists, so that you can sort of have an intuition for when you have missed an edge case. That said, a lot of that comes from writing really carefully. So if you are writing a proof the right way, it should be more clear to you. Still, you may miss things. It should be more clear to you that there was an edge case that you missed, because you are making your assumptions very clear. If you say that, for example, because n is greater than 0, and then you realize, oh, wait, n could be equal to 0, and that would be an edge case that I didn't think of. This is why it's really good to write out those steps and just have all of the logical steps being there, even if they're just mentioned really briefly. The key to a good proof is not belaboring obvious things. It's making all of the logical steps explicit, because sometimes when you don't make those steps explicit, there'll be an edge case that you didn't think of. And professional mathematicians mess up on this as well. Fermat's last theorem was a very famous unsolved problem that was not proven for maybe 300 years after it was first suggested. And when it was proven, the first proof was actually wrong. There was a mistake in it. Andrew Wiles released a proof, and there was a mistake. And he spent, I think, another year or two patching that mistake. And then, fortunately, he was able to fix the proof. But this happens. Hopefully, there will be no problems which you are encountering that require you to patch them for 2 years. But this does happen, and it's not because there's something wrong with you. Are there more questions? Okay, let's get started with probability. This will be the first of several classes on probability. I'm not going to go into the truly formal, definitions in probability. And there are things like measure theory. If you really want to look at probability from a formal perspective, you can do that. But I'm just going to give some fairly rigorous definitions. So a random variable is a variable that takes on different values with different probabilities. Some examples of random variables are the number of heads if a coin is flipped 10 times, or the distance traveled by an arrow after it is fired, or the height of a random person in this class. These are things which can take on different values with different probabilities. So sometimes they are discrete valued random variables, like, for example, the coin flips. A coin is going to take on discrete values. You're never going to have 2.5 heads. It takes on these particular values. Or there are random variables that take on continuous values, like the height of a person, maybe. So a height of a person could be really any number of values. If it's a random person in this class, then maybe it is a discrete number of values from the people in this class. But the height of a person in general could be a continuous value. An event describes a particular set of outcomes for a random variable, or a set of random variables. So if x is the random variable for the number of heads in 10 coin flips, then having exactly 0 heads is an event, and having greater than or equal to 5 heads is also an event. And you can talk about these events as either happening or not. So for example, if you got 4 heads, then neither one of the events would have happened. If you got 0 heads, then the first event would have happened, and the second event wouldn't have happened. Probabilities. So the probability for a random variable taking on a particular value is a number between 0 and 1 inclusive. There is a really important property of probabilities, which is that the probabilities for all possible settings of the random variable have to be equal to, have to sum to 1. So if you consider all the possible numbers of heads that you could get, all of those probabilities have to sum to 1. So you have these non-negative things which sum to 1. This is very obvious, but it's really, really important. Probabilities have to be between 0 and 1, and all the possibilities sum to 1. If the space of possible values is continuous, then this might be an integral. So for example, you might have this. You might have an integral from the minimum possible value to the maximum possible value of the probability that the random variable is equal to a particular value with respect to x. And this here is it's a probability density function technically, rather than an actual probability, but we're not really going to be looking at continuous probabilities as much, at least not in this class, when we get to Gaussians a little bit more. You can think of this as just, the integral is just basically if you had a really large number of possible values. It's basically continuous valued random variables are basically like discrete valued random variables, only you have a lot of discrete points that they could take. So if you're taking all the possible floating point numbers or something. There are a couple of questions. Is there a name for mixed values? For possible outcomes or 1, 2, or 1 to 200? I'm not sure I exactly understand the question, but there could certainly be an event of the random variable is equal to this, or it's in this range. Absolutely. I don't know that there's a particular name for that. Is a random variable different from function over some variables? Yes, it is different. A random variable is just anything that it's like a variable that's random, basically. Sorry, that sounds a little bit stupid, but a random variable is just anything that takes on different values with different probabilities. It's basically like a variable with a probability function assigned to it. It will probably become a lot clearer with examples. If we're looking at the probability of an entire event, so like probability of the event x equals a or x equals b, then if those events are mutually exclusive, then the probabilities just sum together. So the probability of a equals probability of x equal a, or probability of x equal b is just the sum of the probabilities, because it can't be both a and b. This is really obvious. This is just like writing down some things that are intuitively obvious about probabilities. Like the probability that you get either a 5 or a 6 if you roll a die is going to be the sum of the probability that you roll a 5 and the sum of the probability that you roll a 6. Pretty simple. Okay. Independent events. If you have events A and B, then we can write A intersection B for the event that both A and B occur. Now, two events are independent if the probability that both of them occur is equal to the probability that one of them occurs times the probability that another of them occurs. This is another formula that is intuitively obvious to us, but needs to be written down. For example, if you had a coin flip, the event that you get heads in the first coin flip, and you get heads again in the second coin flip, those are two independent events. Because rolling a coin twice, the first one doesn't affect the second one. The probability that you get both heads is 1/4, which is 1/2 times 1/2. And this is how we calculate it intuitively. And the reason why we can calculate it that way is because these events are independent. Here's an example of two events that aren't independent. The first event, get heads in coin flip 1. The second event, get heads in both coin flips 1 and 2. Now, what is A intersect B? In both of these cases, it means when A and B are both occurring. And in both of these cases, A and B both occur if we get coin flips in both, if we get heads in both coin flips 1 and 2. However, in the second case, the probability of A is 1/2. And the probability of B is just 1/4, because B is the same as A and B. B is just get heads in both of the coin flips. So in this case, we don't have 1/4 equals the product of the individual probabilities, because the individual probability is 1/2 and 1/4. These are not independent events. That's because if you flip heads in the first coin flip, you are more likely to have B happen. If A happens, it makes B more likely. It doubles the probability of B, in fact, because B have heads in both coin flips. So these events are not independent. Likewise, you would have non-independent events if you had two coins and for some reason flipping one controlled the other one. If they were like quantumly entangled. I know that doesn't really work, but if you were able to flip one coin and immediately the other one would flip in exactly the same way, then you would have two events that are not independent. Any questions? This is just formalizing some stuff that is intuitively obvious to us. Okay. Expected value. So the expected value is basically the same thing as the mean of a random variable. Sorry, just dealing with a technical issue. One moment. Yes. The expected value or mean of a random variable is just the weighted average. It's the sum over all possible values times the probability that that thing occurs. This is what we talk about when we talk about averages. It's talking about what happens multiplied by the probability of getting that. It's like the expected number of dollars that you get if you have some small probability of winning a huge amount. Then the expected value might be somewhat less because you have a small probability, but it's a large amount. And the idea is that if you averaged many different tries, this is what you would get, because if you have a certain probability of getting X times X, that is what will happen if you sort of roll this random variable many times. The expected outcome, the average outcome over all of those tries will be this. If the variable is continuous, this just becomes an integral. And remember before when we said that the sum of probabilities is equal to 1? This is the same as the sum of probabilities. It's just instead of just doing the sum of probabilities, doing the sum of probabilities times X. So times the thing that it equals. This is how to do an expected value if the random variable is continuous. So here's an example. The expected number of heads, or the average number of heads for a single coin flip, is just the probability of getting 0 heads times 0 plus the probability of getting 1 head times 1. So that's 1/2 times 0 plus 1/2 times 1, so it's 1/2. That makes sense. The expected number of heads that we would expect to get for a single coin flip is 1/2. Some properties of expected value. Again, this is the definition of expected value. So from this definition, it's clear that the expected value of C times a random variable is just C times the expected value. And that's because if you multiply all of these values by C, the probability, you're looking at the probability that Cx is equal to something Cx, something C times bigger, times, you're multiplying this by Cx. You're multiplying this by C, sorry. So if you just scale everything up, the expected value goes up as well. Here is a really important property of expected values, which is, it is very simple and it is just very critical in a lot of situations. Linearity of expectation. The expected value of two variables, the sum of two variables, is the sum of the expectations. This is the case regardless of what those variables are. They could be correlated, they could be independent. We don't need to know anything about them. Regardless, we have linearity of expectation. It's an extremely powerful tool. For example, the sum of two dice. The expected value of that is equal to the expected value of one of the dice plus the expected value of the other one. And we will see some more complicated examples in a moment. But first, why is this true? Why is the expected value of the sum of two random variables equal to the expected value of one plus the expected value of the other? They are not necessarily independent random variables. They could be dependent. In this particular case, they are independent. We will see examples where they are dependent. It's not actually that simple. There isn't a one-liner. Let's try writing it down. And for the question, because expectation is a linear operator, basically yes, but let's write it down. So the expected value of z, if z is the new, let's say new random variable, z is the sum of x and y. The expected value of z is the probability, the sum of the probability of all the possible values of z, probability that z equals that times the actual value itself. That's just the definition of expected value. Okay, now let's consider all the possible values x and y which could have led to this z. What we're looking at is the probability that x is equal to some value x, y is equal to some value y, multiplied by the sum of those things. This is just another way of writing the previous line. We're looking at the probability that you get a thing times that thing. In this case, the thing is the sum. But the expected value is just the probability, the sum of the probabilities that you get things times those things themselves. Okay. Now, let's just break this into two sums. This is the same thing, just broken into two different sums. Okay. Now what we can do is, whenever you have a sum over two things, x and y, you should think in terms of making it a sum over x, then a sum over y, or a sum over y and then a sum over x. This is just one of those mathematical sort of techniques for rearranging equations that you should just, this is something that you should memorize or just like learn is useful. So in this particular case, which is the order that we want to do these summations? We're doing x, then y here, and we're doing y, then x here. They're just the same thing. It's a question of, you have two for loops. You can swap the two for loops around. Which order do you want to do them? It depends upon what your algorithm is. In this particular case, we're going to have the two orders of the for loops in two different orders. So here, what we can see is we're summing over x, and then inside that we're summing over y. So what is this? Well, this is the probability of getting x equals x, and then the probability of getting y equals y for every possible y. So if you sum over all the possible y's, because we know that the probability of many events, all the possible values of y is going to be 1, then we end up with the probability of x equal to x. Likewise over here, because you're summing over all the possible values of x, you get the probability that y is equal to this particular value of y. And then this becomes just expected value of x plus the expected value of y. Notice we didn't use anything about the distribution of x and y together. We just used the fact that if you sum this over all possible values of y, you're going to get probability that x equals x. Are there questions? So this is a reordering can be done in the continuous case as well. Yes, there is a theorem that says that you can reorder integrals. You can reorder integrals with respect to two different variables, and you'll get the same thing. Okay, now let's see how this is useful. What is the expected number of heads in n flips of a fair coin? This is one of those things where our intuition is probably pretty good. Yeah, so if you expect, if you flip a fair coin, so it's equally likely to come up heads or tails, then you would expect it to come up heads about half the time. So the expected value should be n over 2. How can we prove this? Well, the expected number of heads for a single flip we saw before was 1/2. Therefore, by linearity expectation, the expected total number, the sum of the number of heads on each individual flip, is just n times 1/2 is n over 2. Now, these are independent events. The really interesting cases of linearity of expectation come when you have dependent events, events that could depend on each other. A deck of n cards is shuffled randomly. How many cards are expected to be in the same place as they were before it was shuffled? Now, you imagine you've numbered the cards. You know, they started out in order. How many situations do you expect the kth card at the beginning to be in position k after you shuffled it? You shuffled it completely randomly. What are your thoughts? This is a random shuffle. It doesn't matter how it was done, but assume it's a random permutation. So there's a lot of disagreement. I'm seeing 3 different possible values. So what's a good random variable here? What random variable should we define? There's a lot of suggestion of the position of the card. Let's define a random variable that's really like very simple. Like we want to see that the probability of a we want to assess the random variables are things that have different probabilities. So at the very least, we want the random variable that we're taking the expectation of, right? We want at least the x to be the number of cards that stay in the same place. We can define another random variable. Are there other random variables that are useful that can help us get to x? But certainly we want x because that's what we need the expectation of. how could we use other random variables in order to get x? You might be overthinking it. Yeah, let's try to define an indicator random variable. It's just 1 if the card stays in the same place. It is 0 otherwise. What is a particular property of x and xk? Why is this useful? We have an indicator variable. It's just like a coin flip, exactly. X is equal to the sum of all the xk. If card 2 stays in the same place, it contributes 1 to x. Otherwise, it contributes 0. OK. So what can we do now? We want the expected value of x. And we expressed x as a sum of other things. It's a lot of overthinking going on. Xk, unfortunately, does not follow Bernoulli distribution. I mean, yes. Xk is a binary vector, so yes, it is 0 or 1 with some probability. Yes. Yes. So we can work out the expectation of x by using linearity of expectation. That the expected value of x is just going to be the sums of the expected values of the individual random variables xk. And what is the expected value of xk? Yep, is just the probability of, depending on what n is, the probability of staying in the same place is going to be 1 over n, if it's a truly random shuffle. So the expected value of x itself, sorry, this should be expected value of x is equal to n times 1 over n. It's just 1, because you're summing a lot of things that are equal to 1 over n each. Done. Now, this is powerful because these are correlated variables. Actually, if you have one card staying in the same place, it makes it more likely that other cards will be in the same place as well. However, that doesn't matter. Linearity of expectation just says that the sums of the expected values are the same. It doesn't say how often you have many of these things happening. It just says the average. Other questions? It doesn't. The particular. We're assuming that the shuffling is a completely random permutation. In answer to the question about how long is the deck being shuffled. So this is, like, to me, this is still mind-blowing. And we will see linearity of expectation come up in many circumstances, in particular when we look later at the probabilistic method. But it is a really, really powerful tool. OK, so let's look at another problem. A coin has a probability p of turning up heads. What is the expected number of times we have to flip it before the first time it turns up tails? Sorry, I guess I should have phrased this differently. What is the expected number of times we have to flip it, including that first time that it turns up tails? in answer to the question, yes, humans do not shuffle perfectly randomly. We were assuming that it is perfectly random. There are a lot of people suggesting 1 over p. Why is this not correct? This is the expected number of times you have to flip it before the first time it turns up tails. It's not the probability that turns up tails immediately. If it were 1 over p, then you would have, if the probability of heads goes down, then 1 over p goes up, and you expect to have to flip it more times. So it couldn't be something that gets bigger as p gets smaller. This is not a super difficult problem. So it is possible that you are overthinking it. But let's go into it. How could we go about proving this? I know that the first thing that I would probably do in such a problem would be just sort of to play around and see what happens. So I would probably just play around for a bit. We can just get t immediately. And that has probability 1 minus p. We get heads and then tails with a probability of p for the heads and 1 minus p for the tails. We get 2 heads and then a tails. And the probability of p squared times 1 minus p. Any patterns? One minus p times 1 minus p squared times 1 minus p. What is the pattern here? Great, yes, p to the k times 1 minus p. Okay, great. So how can we solve this? A geometric series, I'm going to sum them together. So we have 1 minus p plus p times 1 minus p plus p squared times 1 minus p plus p times 1 minus p. Factor out the 1 minus p times all of this. Great. What happened? Why did we get 1? Is 1 the answer? 1 flip. It's a bit suspicious. What did we do wrong here? Ah, yes, total probability is not expectation. Total probability has to sum to 1. What we just did was we summed up all the probabilities, all the possible things, and we got 1. But that's not telling us anything, because the total probability should always sum to 1. All this is saying is at some point we're going to get a tail. So we've dealt with all the possible probabilities. Great. Okay, that doesn't help. But we can solve for the expectation. So the expectation is going to be some of the probabilities times the number of flips that we needed to get there. So like in the first case, we got tails immediately. So we had 1 flip, 1 minus p times 1. Second case, we had 2 flips, so it's times 2. Third case, we had 3 flips, and so on. Okay, so it's this. And that's not quite as nice. How can we solve this? This is hopefully not equal to 1. It was equal to 1 if we didn't have the 2 and the 3 and the 4 here, if it was just 1 plus p squared plus p cubed. So there are a couple of ways to do this. There are a couple of ways to do this. One way has been to use the Taylor series. I'll come back to that idea in a moment. What is a simple thing to do if you were given this? How to work it out? You could just literally multiply it out. So this is if you multiply this by 1, you multiply this by p. And you just subtract them. Okay. That wasn't actually too bad. So what is the answer? What is the expected value? Yep, 1 over 1 minus p. It is just the geometric series. Okay. So let's go back to here. Another way for you to work out, actually, let's do it here. Another way for you to work out what this is actually to realize that it is going to be the derivative of this Taylor series. I'll let you think about that. But if you take the derivative of this Taylor series with respect to p, then you will get this Taylor series. And so you can work out that if you take the derivative of this function of p, you'll get this function of p. Does that mean that if it is a fair coin, just if you have a coin with a probability of heads 1/2, probability of tails 1/2, the answer is 1/2. If you plug in 1/2 here, it's actually 1 over 1 minus 1/2, so the answer is 2. You expect to need 2 flips in order to get the first tails. Sometimes you'll get it on the first one, but sometimes you'll need many times. So the answer is 2. Is there a simpler approach? Is it a coincidence? I realize that this could be intuitively clear, but this is a pretty quick way to prove this. The number of times before the first thing happens is different from the expected number of things that will go right, the expected number of tails. But yeah, I mean, it could be intuitive here. If you can find a really short proof, I am interested. Okay, so we had the sums of expected values. What about the product of expected values? Is the expected value of the product equal to the product of the expected values? Not in general. Indeed, you need independence. If these are independent random variables, so x being something and y being something are completely independent events, then it is true. So remember, what it means if they are independent is that the probability that both things are equal to things is equal to the probability of one times the probability of the other. In this case, if you let your new random variable be the product, let's write out the expected value. Here, we're looking at the probability that you have values x and y, and you're multiplying the probability by the value, and the value here is xy instead of x plus y. It's just very similar to what we did before. If they are independent, then you can break this down into probability of x and probability of y. And here, this is just breaking out the summation. Since this doesn't depend upon y, and since this doesn't depend upon y, you can just move those outside the summation. And then you can divide it into two summations. Sorry, I realize this goes off the slide. Whoops. This thing is just the expected value of x, and this thing is just the expected value of y. Other questions about this? This is just in the case that the random variables they lead to independent events. We can call those random variables independent. That's just another way to say, another way to use the word independent. If x and y are independent random variables, then this does work. In general, it doesn't. So let's take a look at some examples here. Suppose that x is the number of heads in a coin flip, and y is the number of heads in another coin flip. These are independent events. The expected value of x is 1/2. The expected value of y is 1/2. The expected value of x plus y is, in this case, all four outcomes are equally likely. You have tails, tails, so 0 heads, heads, tails, tails, heads, and then heads, heads. The average of these things is 1. So the expected value of x plus y is 1. What about the product? Well, unless you have both of them being heads, the product is going to be 0. So you have 0, 0, 0, 1. So the expected value of the product is just 1/4. In this case, we have linearity of expectation. 1/2 plus 1/2 equals 1. And we also have these things multiplying together. 1/2 times 1/2 equals 1/4. And that's because these are independent events. Now let's look at dependent events, events that aren't independent. By contrast, suppose that x is the number of heads in a coin flip, and y is the number of tails in the same coin flip. In this case, the expected value of x is 1/2, and the expected value of y is still 1/2. But let's look at the possibilities for x plus y and x times y. The expected value of x plus y is just 1, because either way, if it's heads, then x is 1 and y is 0. If it's tails, then x is 0 and y is 1. But the product is always 0, because you either have 1 times 0 or 0 times 1. So the linearity of expectation works because linearity of expectation doesn't require that there are independent events. It works all the time. So linearity of expectation, 1/2 plus 1/2, again, equals 1. But the product of these things is definitely not equal to 0. Questions?